the convolution theorem. In this section, we introduce the convolution of two functions which are f of t and g of t, and we denote it by f star g of t. The convolution is an important construct because the convolution theorem allows us to find the inverse Laplace transform of a product of two functions. L inverse of f of s into g of s equal to f star g of t. Now we look into the definition. Let f of t and g of t be two functions of t. The convolution of f of t and g of t will be also a function of t, and we denote it by f star g of t, and it is defined by the relation f star g of t equal to minus infinity to infinity f of t minus x into g of x dx. Now we look into an example. We find the convolution if the function f is f of t equal to t into u of t and g of t equal to t square u of t. So here we have to find f of t minus x first. So f of t equal to t into u of t. So what will be f of t minus x? We replace t with t minus x. So it becomes t minus x into u of t minus x, and g of t equal to t square into u of t. So g of x will be x square into u of x. Therefore, the convolution, substituting in the formula, we get f star g of t will be equal to integral 0 to t minus x into x square dx. Integrating, we get 1 by 3 t raised to 4 minus 1 by 4 t raised to 4 after applying the limits from 0 to t. Then the final answer is 1 by 12 t raised to 4. Next example is find the convolution if f of t equal to t into u of t and g of t equal to sin t into u of t. So first we find f of t minus x, that is t minus x into u of t minus x, and g of x equal to sin x into u of x. So here for integration from 0 to t minus x sin x dx, we have to apply integration by parts. So first function into integral of the second minus integral of derivative of the first function into integral of the second function. So we get it as minus of t minus x cos x from 0 to t minus integral 0 to t into minus 1 minus cos x dx. Applying the limits, we get t minus sin t. So the convolution is t minus sin t. Then to find the inverse Laplace transform, we apply the convolution theorem. L inverse of capital F of s into capital G of s equal to f star g of t. This convolution theorem has many applications which include probability, statistics, computer vision, natural language processing, image and signal processing, engineering, and differential equations. The convolution can be defined for functions on Euclidean space and other type of groups. Next, we are doing some problems using convolution theorem to find the inverse Laplace transform. So first one is find the inverse Laplace transform of s by s square plus a square whole square. So we have to find L inverse of s by s square plus a square whole square. So we split the function as L inverse of s by s square plus a square into star L inverse of 1 by s square plus a square. So what is the inverse of s by s square plus a square? We know that it is cos at, and the inverse of the second function is sin at by a. Then by applying convolution theorem, integral 0 to t cos au sin a into t minus u by a du. Here the function is of the form cos a sin b. So we write it as sin a plus b minus sin a minus b. So we get 1 by 2a integral 0 to t sin at minus sin 2au minus at into du. Then integrating term by term and applying the limits, we get the answer as 1 by 2a t sin at. Next is find the inverse of 1 by s square plus a square whole square. So here also the function 1 by s square plus a square whole square, we write it as the product of 1 by s square plus a square star 1 by s square plus a square. So the inverse of both functions are same, sin at by a. So applying convolution, sin at by a star sin at by a. So integral 0 to t, first function sin at by a into sin a into t minus u by a du. Here also we apply the result sin a sin b equal to cos a minus b minus cos a plus b by 2. Then we integrate. Then after integrating term by term and applying the limits, we get the answer as 1 by 2a cube sin at minus at cos at. Next example is find the inverse Laplace transform of s square by s square plus a square whole square. So here we split the function as s by s square plus a square star s by s square plus a square. So we'll take the inverse. The first function and the second function are same. The inverse is same, cos at. So cos at star cos at. So applying convolution theorem, it becomes integral 0 to t cos at into cos a into t minus u du. Here the integrand is of the form cos a cos b, which is equal to cos a plus b plus cos a minus b whole divided by 2. So again applying this result and integrating, we get cos at into u plus sin 2au minus at divided by 2a in the limit 0 to t. Applying the limit, we get the result as 1 by 2a at cos at plus sin at. Then here we have to find the inverse Laplace transform of 1 by s square into s square plus a square. So we write it as L inverse of 1 by s square star L inverse of 1 by s square plus a square. So the first function is 1 by s square, its inverse is t. Second function is 1 by s square plus a square, the inverse is sin at by a. So by applying convolution theorem, it becomes integral 0 to t sin au by a into t minus u du. So we have to apply integration by parts. Sin au by a, first function, and t minus u is the second function. Then we integrate using product rule. T minus u into minus cos at by a minus 1 into minus sin at by a square in the limit 0 to t. Then applying the upper limit t and lower limit 0, the function reduces to the form 1 by a cube into at minus sin at. Okay.